This is question 7. Here we have a system that we've looked at, question 6, and we have a 1-second delay in our system. And the problem is to design a Smith predictor that results in 10% overshoot for step response, basically. So the Smith predictor is a very useful method, and it resembles the model matching methods that you might already know. It shares some properties with the model matching controller in the sense that it is heavily model related. So the Smith predictor uses the model of the system to overcome the problem of delay. Now, let's have a quick review on the Smith predictor. Now, let me run the script first. Now we have GSS, which is 10 divided by s plus 10. And we have a delay term. Let's add that too. Let's say GSSD with delay. GSS times x minus s. So that's basically it. So we have such a transfer function. Now the issue with this is the following. If we use a controller and such a plant and build a feedback structure and calculate the closed loop transfer function, the problem is that we don't get a fully polynomial fraction. Let me demonstrate it. Let's say we have k equals 1, a unit feedback. So if we have that, the closed loop would be GSSD divided by 1 plus GSSD. Now, let's also have simplify. Hopefully, it'll produce some nice results and even maybe pretty to prettify the output. Now, yes, you can see if this is s plus 10, you can multiply it with s plus 10, and here we would have s plus 10. Basically, we have 10 times e to the power of minus s times s plus 10, and then divided by 10 times e to the power of minus s plus stuff. So, yeah, it's very awkward to have a e term, and to have to deal with this is causing us problems, because I cannot think of this as a transfer function, because it is kind of a well, we don't divide two polynomials to each other, so that's basically it. Now, this is not a polynomial. If you have an e term in your expression, then you're not dealing with a polynomial. The definition of polynomial, so a polynomial by definition, has only the powers of s and their linear combination. So therefore, we don't have any polynomial in the denominator in the closed loop. That means that we don't have a characteristic polynomial. So what am I going to assign here? So there are no poles that I can assign, because this is not exactly a polynomial. So the way we deal with this is by approximating e to the power of minus s using the Putty approximation method, for example, and get rid of the nonlinear term that we have in here. So since we use polynomials in the approximation, we end up with polynomials, and it will give us basically a closed loop transfer function. But is there a way of dealing with this in a different manner? Because when we use frequency domain methods, body approximation, body plot, basically, no approximation there. If you use body, it handles this in a nice way because of Euler. Now, is there another way of dealing with such a closed loop? Well, basically, yes. And the way we can deal with this is by benefiting of a structure. Now, if you choose the structure wisely, we can overcome this problem. Now, well, the structure replicates the system model, let's say we have gs e to the power of minus s. So what we are going to do is we are going to replicate this and take the difference of this, and also have another branch that has only the minimum phase part. So like this. I'm trying to sketch it. There we go. Now, this is the actual model, and this is the mathematical model, and then we have this here. So you can safely assume that this would be a difference. So we have the model itself, the actual plant, the system, and then this mathematical model. So we take the difference of that and add to the difference gs. So this is a special structure that we construct. And then there will be the controller itself, and then we will have the output and then the feedback structure as usual. Now, since we take the difference here, the benefit here is that if the mathematical model represents the actual plant, the physical plant, if it's matching it, and that's where I mean the resemblance of the model matching. So if this and this match in models, then they should cancel each other out. If it's a perfect match, then this difference should be 0. And if I add this branch to the 0 difference, I should get only gs. Now, ideally, if they cancel each other out and I have a controller and then gs is the only branch that is active basically, so this loop here should be basically inactive if it's an ideal case. So then I will have fs and then gs and then the feedback structure. The only thing that I wouldn't get rid of is because of the difference and because of the control block simplification, I would get the e term that will still be present, but I would get rid of a very challenging part of the transfer function. So basically, my closed loop that I'm trying to achieve here looks like this. So we would have, let's see, now we would have fs times gs. I'm going to write it out, but I'm going to show you how. Now, fs divided by then 1 plus f times s times, and this is the actual part, gs plus g, so this is base, let's call this g model or g plant, let's call it g plant, the physical plant, plus gs minus gs e to the power of minus tau s. So yeah, this gs is basically the model, it's the plant itself again. So there we go. This would be the closed loop, and once I've shown you the whole connection, the whole structure, hope that this will become obvious. Now here, the assumption is that the plant is identical to gs e to the power of minus tau s. So what you're trying to do is you're trying to model your physical system with the minimum phase part and the delay part. And if you're accurate enough, if you have a very nice model, then this planned, and this difference should ideally be equal to 0. If that's the case, then gs is left here, and you have 1 plus fsgs, which is basically what we use all the time. So if this and this cancel each other out, then we are left with 1 plus fs times gs. And since the g plant, the actual plant, is equal to, or should be equal to this, you can see that this term lives in the numerator, and then we have fs times gs. So something like this. So I can factor this out and write it like this, which would then result in line 19, where I can see that I have my usual closed loop transfer function here. This part is the actual transfer function that we've used so far, and then this is just the delay part. So I cannot get rid of the delay, which makes sense because the system has delay. So even if I do something that is brilliant and get rid of all the mathematical stuff, there is still delay in the system. So if I apply something now, it will happen tau seconds later. So there should be delay in it. So we have the delay part, but it is isolated, and I have this part to deal with. So I can design the system, a controller to the system, to the transfer function gs, with the specifications, settling time, overshoot, rise time, peak time, whatever. And the only thing that the structure will result in is a time shift, and that's it. So the delay will be present, so keep that in mind, and design your controller for only the non-delay part. So this is fairly interesting and also very nice. So if you know the structure, and if you can work out the relation or the transfer function of the closed loop, and if your plant matches your model, then you're good to go. You don't have to think about delay. It will be present in your closed loop transfer function, and you can design your controller for your minimum phase part. And that's going to be it. Of course, there's a flaw, and the flaw is that if this does not match exactly, then you will run into trouble, and hopefully we will demonstrate that in a minute. So let's attack this problem by not even defining the delay part and trying to design a controller. Now, the overshoot value was 10%, and there's no settling time whatsoever. So we can go ahead and design our controller. Let's do that. So let's say, so is there a controller? A system, 1 second delay. So we're not even restricted on controllers, but let's go with the PI controller. So I'm defining KP and KI, and be careful here. I will do this if I use the algebraic method, where I equate the coefficients of PCS and PDS times PES. So the residue times the desired polynomial's coefficients should be equal to the characteristic polynomial equation coefficients. So therefore, I'm using KP and KI. If I would have used the root-locus method, then I would have stick with the K times S plus Z divided by S. So we have this, and then the PI controller with KP plus KI divided by S, and then the closed loop would look like this: Fs times Gs plus 1, and then I would get the numerator, denominator, and then we have the denominator. So let's see. So there we go. It is a second order one, so we could quickly define omega to be real, omega n maybe. And then we have zeta, which should be minus log, and this is log, natural log, minus log overshoot divided by the square root pi squared plus log overshoot squared. Now I have zeta, I have omega n, even though I don't know what the exact value is. 2 times zeta times omega n times s plus omega n squared. And then, do we need PES? Since this is a second order one, we don't really need any. So we can directly form our problem by using the coefficients of PCS. All the coefficients should be equal to coefficients of PDS. And let's look at our problem. Of course, we called it then, so stick with that. So there we go. Maybe using VPA is a good idea because numerical stuff. So there we go. Now I can see that Kp omega n, Ki omega n. So basically we have Kp, Ki, and omega n. Now we can choose omega n basically. So let's look for MATLAB if it gives us some nice solutions. Let's solve it. Now it seems to come up with a solution here where Ki is 0, of course. So yeah, we have to choose omega n. Now let's define omega n equals 1. So let's see what this gives us. Round 7. Problem looks like this. So Ki is 0.1 and then Kp would be, let's see. So Kp val equals, I will solve that, Kp and then Ki, then we have Kp val and Ki val. So, of course, I wouldn't recommend this because it has a negative Kp. So let's try something else. What about, let's have 20, for example. Let's increase it dramatically. Seems to be nice. So 1.36 and 40. Let's quickly determine what the controller is. Of course, I didn't bother with the details of giving settling times and then having nice design requirements and maybe resulting problems, but it's more about the idea than the numerical stuff here. So let's have fs times gs. Let's also look for zpk. So now the roots of this, so we can determine if it's a dominant one. The roots lie here, minus 11, and then we have 29, which is, yeah, I guess it is sufficient. So you have to be aware of the position of the 0. We might go ahead and look for the numerator and then solve that with omega n to get maximum dominance factor. So that would be one way of defining omega n. But for this question, it's not really that important. So we'll skip that for now. So we have fs. Now the whole process is about designing fs, and that's it. We're basically ready for this controller to control our system with delay. We only have to build the structure and we're good to go. We don't need to think about the delay, and that's the nice part here. So I can see that Kp is 1.365 and the Ki is basically 40. So I have already prepared the Simulink model that will show you the structure because it would be too time consuming if I would have done it during the video itself. So now remember this part here, and I will create a subsystem so we don't see it anymore. And let's resize this and call this plant. So this is real life. If you don't see the internals of the plant, you somehow have modeled the plant, and your model is GS times the delay part. So the transport delay here is a 1 second delay, and we have 10 divided by s plus 10. So I assume that this is my mathematical model. So here we have the plant itself, and then I have another branch which includes my mathematical model. Now I take the difference. If this difference is 0, ideally I have my Smith predictor working, basically. Now, if this is 0, I still have another branch where we add the minimum phase part, and then I have my controller here. I can adjust these parameters by 1.365, and the other one is 40. So there we go. Now I have my controller implementation. You have the error, the reference minus the output. You can see that. Here is the error, and then I take the integral of the error times the ki parameter, and then kp times the error itself, combine them to the control signal. This control signal is applied to this lower branch where we only have the minimal phase part, and then we have the mathematical model part, and then also the plant itself has the control signal as an input, and these will be driven to a certain point, and if the difference here is 0, if they are exactly the same, then we will end up with the supposed transfer function, closal transfer function, which is fs times this. So this should be identical in terms of output. If I have, let's get it over here. Let's get rid of this part here. This should be identical for the same input. Before we do that, let's copy this too. So I didn't design my controller for the delay system. I designed my controller for this feedback here, basically, and with the same input. So that's it. This should work, but the only thing should be this transport delay here, this delay in the output, and that's it. This is these connections should be basically equal to each other. So let's see if it works. Let's run our model. Let's open it up, and you can see we have the output that we should have. Now, of course, we might also adjust some parameters of our model in order to increase the accuracy here. Let's make it a fixed step size, and then maybe from the cutoff, and then sample time of 0.01. So let's run it again. There we go. We have our output. Now let's also see what the output of this difference is, because that's also important. Let's run it. As you can see, it is 0. Now this difference should be 0. Now in the plant, let's say that we have 1.2 seconds of delay, and let's return here and run it. Now you can see that this doesn't even work, and the difference is not equal to 0. So it's depending on the delay here. The delay part is the most important part. Let's reduce it a little bit, and let's run it again. Still the same. Let's decrease it a little bit more, maybe 0.5. So just a 5% error maybe. Hope that this one works. So yeah, it starts good, but then after quite some time we have problems here, some issues, which is of course expected because the model is not exactly matching. So if it's even 1%, let's see what then happens. You can see this is tolerable, so having 1% of error is not bad. So basically, let's see this part here. There we go. This is basically the same, but we only have a little bit of delay here. So yeah, the Smith predictor connection is pretty much this. You have the plant, you have this branch here, and then another branch here, and then you take the feedback from the generated output. And by the way, if you think about the part, which part is the controller and which part is actually the plant itself, interestingly, this part seems to be the controller, but your control structure has also these parts in it. So you should think of this as a whole here. So let me pull them here, and let me also bring it here. So this one down too. I messed up, I know, but what I'm trying to say is that you have basically this feedback here. This is the only feedback you have. And then all this stuff, let me get rid of this lower branch here. Now, all this stuff is basically your control structure. So it is interesting to note that, because the first order part here becomes 1, 2. It is copied 2 times. You have the delay part, and then you have also your system itself. So this is a high order control method. You can see that this is a third order transfer function basically, or at least you have 3 integrators to implement this control structure, where the system has only just 1 integrator, because it is a first order system and a transport delay. And that's it basically here. So it is important to note that this is a high order control method. Now, we didn't consider what the delay is and how this will affect us. We just designed the controller for the minimal phase part, and that's it basically, and use the structure. So here in the PDF, we have the transfer function calculation. Now you can define some internal transfer function and then the outer branch, and you can work this out yourself. Basically, you have fs plus and then 1 plus f, then this difference here. If you do some block manipulation, you will get to this. And eventually, this part here plays an important role. We have G0, G plant, and then G0 times the delay part. So this is the important part. And if they are equal, we will reduce down to this one, which is basically the reason why we can design it for the minimal phase part and not the actual delayed part. Now, then we have the controller design methods. So here it is. And then we have this 1 second delay, solution 1, solution 2. It doesn't really matter in this case. Now here is also another depiction where we can see that small model errors can be tolerated by a Smith predictor, but if your delay is not really what you think it is, then you are in big trouble, because it is very sensitive to delay, more than even for the delay than the pole and zero positions, for example. So this concludes this question. So see you at the next question.